would have been very unhappy if this weren't recorded. Okay, so okay, so T is the category of pointed spaces. And J-O is Mandel-May category, in which objects are natural numbers. Now, this is a category that is enriched over T, meaning instead of having morphism sets, you have pointed morphism spaces, and the pointed space of morphisms from M to N is the tome space of the R n minus M plane bundle over OMN, by which I mean the Stiefel manifold of Stiefel manifold of orthogonal embeddings Rm into Rn. Now, if n isn't at least as big as m, then this embedding space is empty. If this number is smaller than that number, then there are no orthogonal embeddings of Rm into Rn. And in that case, the morphism space is a point. It's a vector bundle over, it's the tome space of a vector bundle over the empty set, and that is by definition a point. Tome spaces always have points. You always have the point at infinity. Okay, so what's a spectrum then? The spectrum, an orthogonal spectrum, X is a functor from the category I just defined to the category of pointed spaces, and I will denote the image of n under this functor by X of n. And functoriality implies that we have structure maps like this for all m and n. We have structure maps with appropriate properties. Now, let me remind you that, oh, I didn't say what the bundle was, did I? If you have an embedding of Rm into Rn, then you get an orthogonal complement, which is a copy of Rn minus m. So that's how the bundle is bundle over the Stiefel manifold is defined. Okay, now part of the deal here is let's consider the case where n is n plus 1. Then it turns out that the space, the Mandelbrot space, is simply the suspension of SO m plus 1. And you can map a circle into this in lots of ways. You can think of this as a parametrized family of circles that's parametrized by all of the orthogonal embeddings of Rm into Rm plus 1. So there are lots of maps of a circle into here. So so that means there's lots of maps like this. So this composite is the usual structure map for a spectrum. But in the original definition of a spectrum, you are in effect choosing an orthogonal embedding of Rm into Rm plus 1. Here you're not choosing it, you're considering all possible orthogonal embeddings, and that makes for a nicer structure, it makes for a good smash product, and so on. Now, I want to do this equivariantly. So I want to go equivariant. So let G be a finite group. So let G be a finite group, then TG stands for the category of pointed G spaces. And equivariant, let's say, pointed G spaces and G maps. And T lower G stands for the category of G spaces, pointed G spaces. And continuous maps, pointed maps. So in this category, maps are required to be base point preserving and equivariant. And that means that for any two pointed G spaces, you have a pointed topological space of maps. So, so this category is enriched over T. This category, in this category, you're not requiring your maps to be equivariant. So that means the set of maps from one space to another gets a G action, namely, we have an element in the group and a map from X to Y, then you can do the following. Let me draw a diagram like this. Okay, this is a diagram not required to commute. This diagram is not required to commute. If the map was equivariant, if F was equivariant, that would mean this diagram commutes. But it is not required to commute, which means that map going this way, and so if I start with F and I have an element in the group, then I get another map from X to Y, namely this one. So gamma of F is defined to be gamma inverse. So I have the group acting on the space of maps in this category. So this category is enriched over category of pointed G-spaces. Notice I wrote an upper G here, even though there's a lower G here, is you can check that the composition morphism in this category is an equivariant map. And you can also check that under this action, so I've defined a group action on the set of maps in this category. So this is a G space. So this is a space that with an action of G, and as such, it has a fixed point space. It has a fixed point space. I'll write that like this. And that fixed point set is the set of morphisms in this category. And that's because a map is fixed. A map F is fixed if this diagram always commutes. If this diagram commutes for any gamma, that means F is fixed, and that means that F is equivariant. Being fixed here is the same as being an equivariant map, so you have this equality. Now, so I'm going to look for, so an orthogonal spectrum was a functor from JO to T, and now I'm going to be looking at functors to either one of these categories from an equivariant analog of the Mandel-May category. So I'm going to write that as JG. And that is the category whose objects are orthogonal representations of G. And the and this is a category, this is going to be, this is enriched. This category is going to be enriched over T over G, so I have to tell you what the morphism spaces are. So, what is this thing? It is the following. This V is a finite dimensional vector space in which G acts orthogonally. So, in particular, it's a finite dimensional vector space, which I'm going to note like this. Same for W. And then I can look at this, or this is the this denotes the dimension of V, this denotes the dimension of W. So these are integers, and then I've got this space, this Mandel-May space JO of this integer into this integer as defined here. So this is a space, and it gets a G, and this space gets a G action using the G actions on V and W in a manner similar to what happens here. So this is a G space. But if you forget about the G action, it's the same space that we have in this category. Now, so then let's switch. So now, an orthogonal G-spectrum is a map, is a functor from, we can consider functors either into this category or the other category, and the notation is an object in this category is a representation, and I'll denote the corresponding space by X sub V. And then functoriality says that you always have maps like that. So, as I said, there were two possible target categories here. And that correspond to the two categories associated with G spaces. So that leads to two categories of spectra. So SP upper G is by definition the set of enriched functors from J lower G to T upper G, and then there's SP lower G so you can think of this as G spectra with G maps, and you can think of this one as G spectra with continuous maps. Okay. Now, if you want to talk about model structures, which I'm not going to do just yet, but if you want to talk about model structures, it's only reasonable to do that in, say, this category. It's only reasonable to talk about model structures that play nicely with the G action if you're limiting yourself to equivariant maps. It doesn't make sense to consider it doesn't make sense to consider the category where maps are not required to be equivariant, because, for example, what would a colimit in that category look like? You had a bunch of G spaces. Say a sequence of G spaces with maps between them, but you're not requiring the maps to be equivariant, then you can't, there's no reasonable way to put a G action on the colimit. Or if you had one such map and you wanted to look at its cofiber, that wouldn't have a G action either. If the map isn't equivariant, then you're not going to get anything useful on a cofiber or a colimit or anything like that. So unless you want to ignore the G action completely, you're going to get an interesting model structure on this category, but not on this one. And similarly, there's interesting model structures here, but not here, for the same kind of reason. Now, eventually, I'm going to define 8 different model structures on this category. I'm going to start with the most simple-minded one, and then I'm going to give you 3 different ways to modify it, and these 3 operations can be done in any combination, and it turns out that the model structure that we need to prove the covariant variant theorem is the model structure where you do all 3 of these operations. I'll get to that later. Okay, some more categorical stuff. I'm going to talk about ends and coends. If asked, I will explain what ends and coends are. I'm prepared. I have a page of notes how to explain what ends and coends are. For the moment, let's just say that an end is a particularly interesting kind of limit, and a coend is an interesting kind of colimit, and they're denoted by integral signs. And this notation was invented by Yoneda in 1960. So here's something I can tell you about this category. And I guess the same thing will apply to ordinary orthogonal spectra. So I'm going to talk about morphism objects. These categories are enriched over category of pointed G spaces. One of the 2 categories of pointed G spaces. Oh, I better be careful about this. Anyway, so I'm going to talk about morphism objects. so if I have two, so it turns out, let's talk about this category. It turns out it is enriched over T, just like the category of, see, I've erased it. The category of G spaces and equivariant maps was enriched over T. You have a topological space of morphisms. You also have a topological space of morphisms between spectra. So let's see, SPG is enriched, SP upper G is enriched over T, and so that means if I have two spectra, this gadget is a pointed topological space, and I'm going to tell you what it is. It's an end that looks like this. This is an end. That means, now as I said, I'm prepared to explain exactly what an end is now, what an end is, but for now, let's just say that an end is a certain subspace of the product of all possible entries here. So for each V, XV and YV are pointed G spaces by definition, and there is a set of, there's a space of equivariant maps between them. You have this for each V. And so you have the product of all of them. And if you have a map of spectra, if you have a map, say F from X to Y, at each component you get a map from XV to YV. So the set of maps of spectra is a certain subspace of this of the product of all of these, and that subspace is precisely this end, which is a nice definition. And similarly, here, now G is a subscript. Okay, these are spaces. If you have a pair of spectra, there is a space of maps between them. Now, you may also have heard about function spectra. You may have heard about the spectrum of maps from one spectrum to another. And I will define that, but I have to do a few other things first. Now, the nice thing about this is when I learned about spectra, it was a lot of it was kind of wishy-washy in the sense that things were I only really understood things up to homotopy. And one of the great tools in the subject was the Brown representability theorem. And I'm a Brown student, so I knew that theorem very well. So the Brown representability theorem says that if you've got a functor with certain properties, then there's an object that you're considering that there's some object that represents it and blah blah blah. And so that meant that if you're trying to figure out what the function spectrum is from the spectrum of maps from X to Y, it had to have certain, you could figure out what its homotopy type was, but you didn't really have an explicit description of it. Now we do have an explicit description of it. Notice that right now everything is categorical. There's no mention of homotopy theory. There's nothing homotopy theoretic about it. This is all categorical, and it's really about, in each case we're looking at, this is the category of functors from here, enriched functors from here to here. This is a category enriched over TG, T upper G, and we're mapping into T upper G. This is a category enriched over T upper G, and we're mapping into T lower G. Anyway, these are categories of enriched functors, and all you need, and there's nothing, in a sense, this has nothing to do with homotopy theory, this is all categorical. You could make similar definitions with replacing these by suitable categories as long as the source category is enriched over the target category or something roughly like that. So some more definitions. Okay, for each V in this category, define the Untitled spectrum which I will denote by S minus V as follows. So this is supposed to be a spectrum. That means it's supposed to be a functor from this category to one of these two categories. So I have to tell you what it is on, I'm choosing a V, so I have to tell you what it is on each W. So here it is. I have to tell you what the W component of this thing is, and it is the following. It's that space. And then the structure maps sort of follow automatically. It's supposed to have structure maps of an appropriate, appropriate sort, and you can figure out what they are. They're related to composition morphisms in this category. Anyway, this is a well-defined spectrum for each V. In particular, let's look at the very simplest case. Let's suppose V happens to be 0. V is the zero-dimensional vector space. So my notation for this is S minus 0, and its W component is this, and that is precisely S upper W. That's the one-point compactification of, remember, W is a vector space on which G acts, and it has a one-point compactification, and that's what this is. Now, so this has another name. This is the sphere spectrum. This is the sphere spectrum we all know. So this is my notation for the sphere spectrum. Many papers about spectra have been written where the sphere spectrum is denoted by S upper 0. That's confusing because S upper 0 also stands for a two-point space. This is not the two-point space. This is something entirely different. Okay, so I call these Untitled spectra because this is a Untitled functor for the object V, and they are key elements in this theory. So let me emphasize again: there's no hand waving here. This is a well-defined. Each one of these is a well-defined space, and it's easy to work out what the structure maps have to be. This is completely rigid. There's nothing up to homotopy. This is still categorical. Now, Now, let's say X is a G-spectrum, and you can think of it as being in either one of these categories. It doesn't matter for what I'm about to say. And K is a pointed G space. Then we can define the smash product of K with X. Now remember, this is a space, this is a spectrum. I'm smashing a space with a spectrum. So I'm going to tell you how I do this. I have to tell you what each component of it is. And it's that. So I smash every component with K. I have a spectrum X. I smash each component with it of K, and I get a new spectrum. And this will have the appropriate structure maps. I can also, now in categorical language, this is known as a tensor. So category theorists would say SP, let's say SP upper G is tensor over T upper G. So that means you can take something in here and multiply it by something in here, as I've indicated. And then there's a dual notion that goes like this. X upper K. You're supposed to think of this as maps from K to X. And the way this is defined is that. So this is a point of G, for each V, this is a point of G space, this is another point of G space, and I can consider maps of K into V, with or without an equivariant condition. So, so a category theorist would say that that SP upper G and SP lower G are both cotensored over that. Okay, so this is called cotensoring, this is called tensoring. Here, remember, we have these ends here. Ends, I remind you, are special kinds of limits. Now I'm going to give you a coend, a useful coend, and that is the following. So there's something called the tautological presentation of spectrum X, and it is the following. X can be written as a coend, which means I'm supposed to write. Superscript means coend. Subscript means end. Unfortunately, Jacob got that wrong in higher topos theory. There's a point in higher topos theory where he defines coends and writes them like this, going against McLean and every other author I know of before higher topos theory appeared. And so now all the people doing factorization homology are talking about coends over manifolds or something, and they write their subscript. And they write as the subscript instead of a superscript. And they say, well, it's too late to change it. But Jacob, I think Jacob blew it.
If you maybe you have a reason.
What?
If you tensor two modules over a ring, a left and a right module.
I probably shouldn't say this on air. I'll talk to you about this afterwards. I do have an answer to that, but I'll say it.
What I was going to say.
Well, what were you going to? Okay, we'll talk about this after. Okay, so what is this coed? It is the following. You take xb and smash it with s minus b. Okay, remember, this is a spectrum I've just defined. This is my Yoneda spectrum. And this is a space, and I've told you how to smash a space with a spectrum. Turns out that any spectrum x is isomorphic to this coed. And that's handy because in some sense it means the only spectra you really need to understand are these. Now, here's something better. Now I'm going to tell you how to define the smash product of two spectra. Okay, so recall the Day convolution theorem. So I mentioned this last time. It was proved in 1970, and it gives us a airtight way of defining smash products of spectra. The point here is that, let's look at this. This is a symmetric monoidal category that is enriched over this category. And we're looking at functors from here to here. So this is a closed symmetric monoidal category. This has Cartesian, I guess, smash product. This has smash product. This is a closed symmetric monoidal category. This is a symmetric monoidal category that is enriched over this. That is, the morphism objects in here are objects in this category. Whenever you're looking at functors of that sort, there is the category of functors itself is a closed symmetric monoidal category. So this is a closed symmetric monoidal category, as is this. And this is a categorical statement, and this is proved by category theory. So so in the case at hand, it says the following: SPG and doesn't matter whether it's superscript or subscript.
Do you not need, for SP lower g, do you not need T lower g to be closed under colimits?
Do I need what?
Do you not need T lower g to be closed under colimits?
I think the way I sneak around that is I ignore the G action. I say, okay, let's just think of these things as functors in T, as T-valued functors. I think that's the workaround. But you're right. I need a the category is supposed to be co-complete. So you're right. Technically, this isn't co-complete. So maybe let's just do it this way. Okay. Yeah. The hypothesis that I need is that this is, in addition to being closed symmetric monoidal, it's also co-complete. It has to have co-limits. Okay, so SPG is closed symmetric monoidal. And the structure is defined as follows. So, okay, so, if I have a pair of spectra, X and Y are both functors from here to here. So if I combine them, I get a map, I get a functor like that. And then, oops. Okay, so I'm just taking the Cartesian product of the two functors. Then here I have the smash product, which gets me here. And on this side, I have the symmetric monoidal structure on JG that has to do with direct sum of representations. And I'm looking for a map like that. It's supposed to be XY. It's supposed to be a functor from here to here, and it is the left con extension for this diagram. And left con extensions can be explicitly described as coends. I'm going to give you some formulas for this in a moment. Where is this? Okay. Okay, so here's a more explicit description of this thing. More explicitly, I'm going to tell you what the Wth component of X smash Y is. And it's a coend. It looks like this. So it's a coend over the product of JG with itself and there it is. Okay, now notice these three guys are spaces. And so this is a coend involving spaces. And coends are colimits that's defined to be a certain co-equalizer. And what that means is that this coend is a certain quotient of the one-point union of all gadgets that you see here. One-point union of all such gadgets. Now, let me point out that this one-point union is actually finite because, remember this thing, this morphism space in the Mandel-May category is a point if W is smaller than this direct sum. Wait, I didn't say that the right way. Oh, yes. Or let me say it this way. It's a point if this direct sum is bigger than W. Now we're doing this for a fixed W. So that means there's only a finite number of pairs like this for which this space is something other than a point. In most cases, if you just pick large V prime and V double prime, this space will be a point and you won't don't contribute anything to it. Anyway, this is a coend, and it is in fact a finite coend.
Isn't there in
I
fact
think
a cofinal subset where V prime plus V double prime is isomorphic to W?
Exactly.
Probably.
Yeah, that's exactly the point.
Yeah, right.
Why is the finiteness important? I mean,
Well, it isn't really. It's a restriction that gives you confidence. It's meant to give you confidence. It's not mathematically essential.
Well, except
But if
you
you're a
haven't yet
tortoise,
said-
this is supposed to make you feel good if you're identifying with the
You
tortoise.
haven't yet said what a space is.
What?
You haven't yet said what a space is.
Do you want me to talk about? Or you're like,
Hausdorff, compact Hausdorff.
okay, so
weekly,
they're
et
weekly.
cetera,
What
et
is it? I
cetera.
think my lawyer wants me to say this. I'm
Exactly.
talking about compactly generated weak Hausdorff spaces.
Okay, so
Yeah, that's what
That's
those are.
fine.
Yeah.
knowing things like finiteness might be helpful.
Yes, okay, now, there's also a way to describe this without the subscript. So without the subscript, the statement is this. So here, oh, I put here, this is omega spectrum. Okay, this is a description of the spectrum. So here, this is a spectrum, and I'm smashing it with a couple of spaces. So, okay, so that's the smash problem. Now I can tell you about function spectra. So, until I saw this, I had never thought of function spectra as anything. I thought of function spectra as just things that were defined up to homotopy. We know what the homotopy is because of Brown representability. Blah, 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 blah. That was the only way I could think of it. But now,
We have a lecture at 3.
what?
At 3 o'clock?
Yes.
We have
Oh.
5 minutes though.
Okay.
Okay,
Thank you.
5 minutes. Okay, I will write down that definition and then quit. Thank you. Okay, so, where are we? All right, so when you have a closed symmetric monoidal category, you can write something like this. And this object is the function spectrum. So what we learn from this is the following. If I want to know that its Vth component, it is the space of morphism, the morphism object as a space from S minus V smash Y into Z. Now X, Y, and Z are all spectra here. X, Y, and Z are all spectra. This is another spectrum. This is the smash product of two spectra. We know how to define this, and we know how to define morphism objects. Remember, this can be defined as a certain end that I wrote down before. So I will stop there. And I'd like to do this again at 2 o'clock on Monday, and hopefully I'll be able to start talking about model structures.
Make sure that it's officially.
Yeah, I'll make sure that it's officially. I thought Paul or John had taken care of that. I guess they didn't. Okay, so 2 o'clock Monday.